Hello, everyone. So today we're going to start the second part of the biological or bio-inspired materials or biomimetic materials. And in this for this part of the lectures, I have shared with you two things: a PDF file of my handwritten notes. That's about the basics of very basic introduction to fracture mechanics and also methods to evaluate self-healing. And there's another PowerPoint that I've shared with you, um, which is about the concepts that appear in self-healing. So without further ado, I would like to start with the presentation that you already have. So we called it materials for self-healing and beyond. It will become clear by the end of the whole set of presentations, what I mean by beyond. So, but a little bit motivation behind why we're doing this, why this field, and then going beyond started. Basically, if you look at nature materials, you see some very interesting phenomena. For instance, if there's a scratch on your skin and it's bleeding, it triggers a set of reactions that eventually leads to turning the blood from liquid to gel, and then eventually, after a few days, the skin is recovered. And so even if you don't pay attention to it, even if you don't put bandage on it, if you don't cover it, it's going to do it for itself in a lot of cases. Now, if you look at traditional engineered materials, composites or metals, they are susceptible to cracks. Okay, so small cracks, micro cracks that form during the lifetime of a structure come together, they grow and they coalesce and form larger cracks, which eventually the material will fail. Now, if your goal was to stop these failures, you need to, in a traditional approach, you need two things. You need to be able to locate cracks and micro cracks, which in a lot of cases, it's going to be very difficult because some micro cracks that are precursors of larger cracks are very small. The second thing you need to do is, after you find them, you have to go there and fix it. So this maintenance requires identifying the location of the cracks, the size of the cracks, and then reaching there and fixing it. Now, imagine a structure that is subjected to cyclic loading, yet it can have fatigue and micro cracks can develop inside it. Even if you could locate the inside micro cracks, it's very difficult to reach them and repair them. A lot of cases, you may end up just replacing the parts. So you see the contrast between this engineering materials and the biological materials, the way our body tries to heal itself. And this is a technology that, and a lot of science behind it, that people try to be able to develop materials. A lot of the effort was on composites, polymer-based composites, to repair them, to give them the capability to repair themselves without us knowing where the cracks are, if the material could respond to an existing crack that is developed inside it and close the crack and heal itself. Now, you may think of it as just mechanical load bearing. And as a matter of fact, that's where the thing started, but it doesn't have to be only that. In many structures, the function is it could very well be dependent on electrical conductivity. And if microcracks develop inside the material, basically you may need to trigger a mechanism that would recover that would regain these electrical properties. Now, there were two waves of this self-healing approach. One is what I would call an intrinsic self-healing approach, and I will explain that in a lot more details. This goes back to about 1980s, and there has been recent efforts on that as well. There is the second aspect of it, which is extrinsic self-healing. A material is not self-healable by itself, but you add some things to it to impart that self-healing capability. And this second phase started after year 2000. Some of the pioneers, you can find it in this link that I put for you here. Oops. You can basically, the video is in this link, is in YouTube. The pioneers were a group of scientists and engineers in University of Illinois. Among them, or the leading scientist or engineer was Professor Scott White, the late Professor Scott White. And there's some very nice schematics that, or cartoons that show how this repair can work. And that's for the extrinsic part. I strongly advise you to look at it and get a feel for it. But to explain the differences between the two intrinsic and extrinsic self-healing, I put some schematics together. So basically intrinsic, as I mentioned earlier, the polymer can heal itself without any additional agents. So imagine this blue thing is my polymer, and it has some cracks in it that has developed in it. And you do something to it that it goes from here. Let me bring my notes back. It goes from here to here. Basically, crack gets closed. And this is a concept that, again, if you look at this video, this is from NASA. So at this point, I would expect you to stop this video and look at the video that I'm talking, and go and open this link and look at this video there. There's a group of scientists in NASA that are looking at space habitats. And they're like, imagine there is some particles from space, just rocks and particles from meteorites. They hit they puncture the space habitat. If the material there's some materials that have the ability to use the kinetic energy that they get from the particle, from the projectile. And as a result of that, the temperature after the projectile, after this rock penetrates the material, the kinetic energy of it will be partly delivered to the polymer. The temperature of the polymer will go up, and now chain mobility will go up, and then it can heal itself. We will explain the mechanisms of intrinsic self-healing in the handwritten notes that I will share with you. But the extrinsic self-healing that I mentioned, that was pioneered by the group in University of Illinois, is, imagine you have a polymer like this that cannot heal by itself. But you add particles like that The orange part, the inside, is a liquid that, if, for instance, interacts with blue, turns into solid. Now, this black thing is the shell that protects the liquid, separates it from the rest of the polymer. Now, if this crack grows, it punctures some of the particles, the liquid will be released and the crack will be healed. So this is intrinsic, this is extrinsic in a nutshell. We identify self-healing efficiency as this. There are two ways we can define self-healing efficiency. One is the ratio of a property of the healed material, the change in the certain property of the healed material with respect to the damaged property, compared to the case before any damage was incurred to the material. So, for instance, imagine in this case, I measure certain strength in the material. I call it F virgin. After the crack grows, at this stage, before any curing has happened, I measure another property, another strength of the material, and I call it the strength of the damaged. Now I heal it, and I measure another strength. So, and I then compare it with the change with respect to the damaged case, that is in both cases, it's in the denominator and the numerator. And so basically, this self-healing efficiency tells me how much of the initial strength was recovered as a result of the healing. If you're doing fatigue experiments, basically you can define more or less the same factor. Here, N is the number, N healed or N controlled, is the number of cycles that at a certain load, the material can survive. And so in the case that there is no healing, basically you will get 0. In fact, fatigue efficiency will be 0. And in ideal case, you can recover all the performance back. So I am going to stop this video, and we are going to continue on the intrinsic self-healing.